Hi, my name is Xiang. Today I will present a paper called Virtual Multi-View Fusion for 3D Semantic Segmentation. The paper is recently published by scientists at Google Research in June 2020. They propose a new method of using multi-view fusion by adding virtual images to tackle 3D semantic segmentation and achieve a state-of-the-art result. The motivation to study 3D semantic segmentation is because its wide range of application. In autonomous driving, robotics, or biomedical imaging, we are often interested in surrounding objects' different location and shapes. The main problem in 3D semantic segmentation is to extract the 3D geometry for a region of interest through segmentation. We need to understand the object's shape, category, and their position. There are challenges in surface determination in the 3D. And previously, there are three major approaches. The first one being multi-view labeling in 2D, and the second one is very popular using native 3D convolutions, and the third one being creating synthetic data. Before I dive deep into this paper, I'd like to give a general background on the scanner dataset that the paper is based on. This dataset is originally published in 2017. It is a richly annotated 3D reconstruction of indoor scenes. It contains 3D camera poses and extrinsics. The general approach workflow is given user an iPad to create an RGB depth scanning. It is then uploaded as a video stream to create a 3D reconstruction and segmentation. And then by using crowdsourcing, they then added the semantic labeling and retrieval and alignment. The scanner dataset has been the most popular benchmark to evaluate 3D semantic segmentation, and the main metric to evaluate them is the 3D IOU intersection over union. We can see the three different major approaches has very different performance result. The earliest one being multi-view CNN, such as ScanNet. It used a 2D to 3D projection, but their performance is often restricted by limited field of view. They are not scale invariant, and in certain views, the lighting is not great. Then the industry moved on to use the native 3D convolution such as 0.9++, and especially the sparse ConvNet has provided a great performance gain that almost double it in 1 year. More recently, we have the 3D spatial temporal ConvNets, which is extension of the 3D ConvNets. This paper is also often referred as Minkowski net. And lastly, we have the virtual multi-view fusion approach that we are discussing today. There are two interesting papers that are also worth mentioning. The 3D Envy is created by the same author of the scanner dataset, Dr. Dai. She used a multi-view method that can be essentially break down to a 2D network and then pass on to a 3D network. This multi-view approach does not achieve a great result, a performance as we can see here. And then the Facebook research proposed the submanifold sparse convolutional networks. It used point cloud as 3D representation and voxel features and coordinates. It then used the sparse convolutional network, which is very efficient on memory usage. The major contribution of this paper we are discussing today is solving the 3D semantic segmentation with state-of-the-art performance. And they achieve that with a simpler classic model without creating a complex architecture or models. The key innovation of the author is that they use 4 steps in data augmentation, including adding the virtual multi-view images. The general approach of the author is after taking the input mesh from the scanner dataset, they created several virtual views of render images. Those images are then passed on to 2D convolutional neural network to extract the 2D semantic features. Those features are then projected back to 3D space using 3D fusion and then create the output label mesh. The first step in their feature engineering is they added the virtual multi-view synthesis. The real images views are often limited by physical restraints such as the distance and physical barriers such as wall. However, virtual views do not have such restraint and can be pulled back from sync, pulled back at any distance. The author then added the additional channels. In addition to the RGB and depth channels, they added the normal to surface channel and global coordinates. The benefits of global coordinates is that they are invariant to different views and has only one representation in one scene. The third step is expanding the higher field of view, and by doing so, they can achieve a larger spatial context, such as when we're comparing from the original view to the virtual view with a higher field. The fourth step is using view sampling. Theoretically, you can create unlimited amount of virtual views in one scene. However, the author carefully select a wide range of views as represented by the blue camera icons here. The green lines in the images are the original real images camera poses. The next step after the data augmentation is to use transfer learning from 2D CNN. By doing so, the author can leverage a larger 2D data set to train from, such as ImageNet and COCO. The author used exception network, which is an improvement from the Inception version 3 model, and they use the depth-wise separable convolution to achieve great results on segmentations. The last step in their approach is to do a 3D fusion of 2D features. They are projecting those features from 2D back to 3D. They render depth channel on virtual views and project back to each virtual views according to their different depths. This paper achieved a state-of-the-art results. It is ranked first place on ScanNet validation set and second place on the test set. And if we look at the qualitative result, their semantic segmentation prediction is almost identical to the ground truth, except some of the very minor details here. It is interesting that the author also did a ablation study for their data augmentation steps. So comparing to a baseline performance of 60%, by adding virtual views, they boost their performance by 3%. And by adding normal views, normal channels and global coordinate channel, they increase performance by another 3%. And by adding higher field of view, the performance increased by 2%. And by adding view sampling, the performance eventually come up to 70%. There are several limitations of this paper. First being it requires a highly articulated feature engineering, which is very time-consuming. Also, this method might work well with indoor 3D data. However, it might not scale well to outdoor 3D data. And then this method also has a high computation cost on simulations, such as generating the virtual views and higher field of views. It does not require that much training times since they are using transfer learning. And lastly, there are noise and distortion exists on the virtual images created by the authors. So to recap, this paper is solving the 3D semantic segmentation problem with a state-of-the-art performance that achieved by simpler classic models using multi-views fusion. The key innovation of the author is that they take 4 steps in data augmentation, including adding virtual view, multi-view images. Their work reopened the direction of multi-view for future research. Thank you. That's it for my presentation. And then Andre will briefly provide a critique of this paper.
Although this paper does show state-of-the-art results, there are a couple of limitations that we would like to address. The first being that there is no verifiable implementation that we can use to check their results and see how it performs on different data sets. The next issue is that there is no analysis on how much memory and how much runtime is required to run this algorithm, so that we don't know actually how tractable it is or what situations it would be practical to run. The next 2 issues are related. The first being that it has a fundamental assumption that the data is coming from stereo image pairs in indoor environments, which is not always the case in the sense of larger outdoor environments where the data is taken from a LiDAR sensor. It's much more sparse and would require many more views. And there's no real analysis of how well that would run on that environment. In terms of other papers, because it's a relatively new paper, there aren't very many critiques. However, there are 2 in particular that we would like to address. The first addresses the way that they sample the views, saying that using random or uniform sampling isn't the best approach. And the second one argues in a more general sense that whenever you do a projection from, let's say, 3D to 2D, you're losing geometric information, and thus you are fundamentally limited in your approach.